the Unit 4 Review Day number 2 warm-up. And in number 1, they give you f of x, and they say find the x values of the mins and maxes of f of x. So we should probably do a first derivative sign chart. So if we find the first derivative, we get 4x to the third minus 36x. If we set it equal to 0 and solve, I think we can factor out what these terms have in common, a 4x. So we'd be left with x squared minus 9. Could probably further factor that into x minus 3x plus 3. So we would get x equals 0, x equals 3, and x equals negative 3. So then we could put those values on a sign chart. We should always label the sign chart, first derivative, and our values are negative 3, 0, and 3. And here on our sign chart, I would put 3 parentheses on each interval to represent these 3 parentheses. And then we can choose numbers to plug in on each interval. So on the first interval, negative infinity to negative 3, a number like negative 4 would probably work. So if we plug in negative 4 into the first parenthesis, 4 times negative 4 is a negative number. If we plug in negative 4 into the middle parenthesis, negative 4 and negative 3 is a negative number. If we plug in negative 4 to the last parenthesis, negative 4 plus 3 is a negative number. Of course, 2 negatives turn to a positive. However, we still have 1 negative left over, so overall that interval is negative. On our next interval, negative 3 to 0, an easy number to plug in would be negative 1. If we plug negative 1 into our first parenthesis, 4 times negative 1 is a negative number. Negative 1 minus negative 3 is a negative number. Negative 1 plus 3 is a positive number. All right, negative times a negative turns positive. All right, so overall that would be a positive interval. From 0 to 3, an easy number would be 1. If we plug in 1 to the first parenthesis, 4 times 1 is 4, so that's positive. 1 minus 3 is a negative, and 1 plus 3 is a positive. So overall we get a negative. And then our last interval, 3 to infinity, a good number would be to plug in 4. In our first parenthesis, 4 times 4 is a positive number. In the middle parenthesis, 4 minus 3 is a positive number. In the last parenthesis, 4 plus 3 is 7. That's a positive number, so we get a positive. All right, so we're supposed to find the x values of the mins and maxes. So we need to look at, if our derivative changes from negative to positive, that means we have a minimum. If our derivative changes from positive to negative, we have a maximum at 0. And then we have another change from negative to positive, so that would be another minimum. So if we write our answers, right, we would have minimums, right, occurring at negative 3 and 3, and a maximum happening at x equals 0. So that's the answer to number 1. State where f has a minimum. So be really careful. Read carefully, all right? This graph is f prime, and we want to know where f has a minimum. So we're not looking at a minimum on the graph in front of us. We need to remember, where f has a minimum. So, you might want to think about your chart. Remember that. Increasing, decreasing, max, min, flat. All right. When your original function is increasing, derivative is greater than 0. Decreasing, less than 0, equal to 0. That's probably the only part of the chart you need. All right. But basically, we're asking for where does f have a minimum? Well, f has a max, min, or flat, one of those 3, when the derivative equals 0. The derivative is what we're staring at. So where the derivative equals 0, all right, the derivative equals 0 at all these values, all right, but remember, we only want a minimum. All these values could be either max, min, flat. We need to figure that out. So what I would do is a sign chart. I think it's so easy once you have the sign chart to just look at your signs, negative to positive like we did above in number 1. So what I would do is I would almost transfer this graph right here into a sign chart of the graph. All right, the values where you have x-intercepts, those are your zeros. That's what you would put on the sign chart. And the sign chart just helps you to organize your information. All right, then think about each interval. All right, from the very left to -3, that's this right here, your graph is negative. So that interval is negative. All right, in between -3 and 1, and in between -3 and 1, your graph is above the x-axis. So in other words, that's a positive interval. In between -1 and 2, right, in between -1 and 2, our graph is below the x-axis. So that's a negative interval. In between 2 and 4, our graph is below the x-axis. That's a negative interval. First derivative is negative. And then 4, right, that graph goes above the x-axis, so it's positive. So I think just kind of writing it that way helps me to figure out, okay, -3 is a minimum, -1 is a max, 2 is not 2 is a min, 2 is a flat, right? It doesn't change. It goes from negative to negative, so 2 is a flat zone, and then 4 goes from negative to positive, so that's a minimum. All right, remember, we were just looking for where our original graph f of x has minimums, so that's -3 and 4. So x equals -3 and x equals 4. Those right there would be your final answer. The sign chart is not necessary. You could just know from the graph, because, okay, your graph goes from below the x-axis to above, all right, that would be a minimum. But the sign chart just helps you to organize your information and kind of allows you to do, a different type of problem that's presented in a different way, the same way you would have done it with a sign chart like you did in number 1. So up to you how you want to do it. From review number 2. So in number 1, it says find the critical points. So critical points are where your derivative equals 0. So we got to take the derivative. This is, of course, chain rule. So derivative of ln is 1 over whatever you're taking the ln of. All right, times, we got to multiply by the derivative of the inside function, which is 4x. So we really get 4x over 2x squared minus 2. All right, and critical points are where your derivative equals 0. So set this equal to 0 and solve. Probably the easiest way, I'm going to put 0 over 1. If you cross multiply, you get 4x equals 0. You could divide both sides by 4, and you get x equals 0. So x equals 0 is one of your critical points. All right. Also remember, critical points are where your derivative equals 0 and also where your derivative is undefined. Right, so what would make your derivative undefined is when your derivative's denominator equals 0. So you also have to think about that. Set your denominator equal to 0 and solve. So you get 2x squared equals 2. Divide both sides by 2. You get x squared equals 1. And you square root both sides. You get x is plus or minus 1. So those are all your critical points. So our answer would be E. All right, let's take a look at number 2. Where is f of x concave down? And they give you the second derivative. So think about, normally to figure out concave down, I would do a second derivative sign chart. So they're kind of already ahead of us. All right, they took the second derivative, gave it to us, so we just have to set it equal to 0. Get x equals 3 and x equals -1. And we could do a second derivative sign chart. Label it the second derivative, put your values on there, -1 and 3. And in terms of the parentheses, I would not worry about putting this x plus 1 squared on there, because anything squared, whether it's a negative squared or a positive squared, you're getting a positive number. And positive numbers don't really influence the sign. So I would really only put this one parenthesis, right, on each interval. And we can plug in numbers. So on the first interval, maybe you plug in a number like -2. -2 minus 3 is a negative number, so overall we get negative. If we plug in a number between -1 and 3, like 0, 0 minus 3 is a negative. And then if we plug in a number like 4, 4 minus 3 is a positive. All right, so if we're looking for concave down, concave down happens where we have our second derivative being negative. All of this right here. So really negative infinity to 3 would be answer choice B. Let's take a look at number 3. Suppose 2a minus 4b equals 10. What is the minimum value of a times b? First of all, I always like when the function has a name, all right? A times b, literally give it any name. Let's call it p. P equals a times b, all right? It's just sometimes easier. So if we're trying to find the minimum value of p, all right, we're going to take the derivative of p. We don't want to take the derivative yet because we have two variables on the right side. We've got the a and the b. So we want to rewrite it in terms of just one variable, all right? Maybe this equation right here, this 2a minus 4b equals 10. Let's solve it for b. We're going to substitute in, all right, for b so we can write p all in terms of a. So if we subtract 2a from both sides, then we can divide everything by -4. So we end up with b equals -5/2 plus 1/2 a. So that's what we can plug in here for b, -5/2 plus 1/2 a. All right, now we probably want to simplify p. If we distribute, we get -5/2 a plus 1/2 a squared. All right, and that looks like we're ready to take the derivative. So if we take the derivative, it's going to be called dpdA equals -5/2 plus, we bring the 2 out in front, the 2's cancel, and we just get a. All right, so next we set it equal to 0 and solve. If we add 5/2 to the other side, we get a equals 5/2. All right, so that's our a value. We need to go back and find our b value. So we have -5/2 plus 1/2 a. We need to plug our a in, which is 5/2. So we have -5/2 plus 5/4. All right, we might want to get a common denominator there. So we can multiply the first fraction by 2/2. So if we do that, we'll get b equals -10/4 plus 5/4. Or in other words, -5/4. So that's our a and our b. All right, but we're trying to find the minimum value of a and b. Or, sorry, minimum value of a times b. So the very last step, a times b, we got to actually multiply those together. So our a was 5/2, our b was -5/4. If we multiply those together, we get -25/8. This is our minimum value of a times b. So the answer is D. And derivative graph, so I would probably label that. I think it is labeled right here, but it might be hard to see. So just to remind you, that is the second derivative graph, and they want us to state the inflection points of f of x. So normally how we'd find inflection points, if we were just given, f of x, what the actual function was, all right, we would do a second derivative sign chart. Right here, we're given a second derivative graph, so I might just turn it into a second derivative sign chart to kind of help me organize my information. All right, but we're staring at a second derivative graph. All right, the x-intercepts right here fall at -3, -1, 4, and let's say that last one is at 6. It's kind of hard to see. All right, and let's just chart out the signs. All right, it starts on the left up till -3 below the x-axis, so it's negative. Then the graph in between -3 and 1 and -1 stays below the x-axis, it stays negative. Between -1 and 4, our graph is still negative. Then between 4 and 6, it goes positive. And then after 6, it looks like it goes negative. All right, so given the graph, figure out the inflection points. Inflection points are where our second derivative changes sign. So at -3, there's no change in sign, negative to a negative. That's not an inflection point. At -1, again, no change in sign, negative to a negative. At 4, we have negative to a positive, so 4 is an inflection point. And then at 6, positive to a negative, there's a change in sign, that's an inflection point. So our inflection points are at 4 and 6. And let's see, 4 and 6 is not an option, 4 and 6.2. So maybe, that last x-intercept was at 6.2. It didn't look like it was at exactly 6. I know I scribbled all over it, but if we look back, it did look a little bit past 6. So 6.2 probably makes sense. So that's why the answer would be C. Let's look at number 5. At a rate of 1 feet per second from a bridge that's 15 feet above the water, at what rate is the angle between the line and the water changing when 25 feet of the line is out? So let's try to draw a picture of this. So let's say this right here, right, is our bridge. Right, a bridge is kind of high up in the air. Let's say someone is standing up here and they're fishing, all right? Let's say the water is down here, right? And they've got this fishing reel reeled out. Again, it's probably a right triangle here. So let's label our sides first of all. Say this is X, anything vertical is Y. Hypotenuse is usually Z. All right, so this right here is our fishing line. So it says the fishing line is reeled in, at a rate of 1 feet per second. So that's how Z is changing. So that's dz dt equals 1 feet per second. And think if that's being reeled in, coming back into the person, all right, that means they're pulling the fish in. That distance Z is getting smaller. So I believe that should be a negative number. Then they said the bridge is 15 feet above the water. So Y is 15. And it says at what rate is the angle between the line and the water changing? So that angle is right here, theta. So that's what they want to know. D theta dt when 25 feet of the line is out. So Z is 25. All right, so right now we could do Pythagorean theorem to find the third side. If you do that, let's see what we get. You get that the bottom of the triangle is 20. Right? So if we're trying to find d theta dt, we're dealing with a right triangle. We're probably talking about SOHCAHTOA here. Right? And think, choose wisely what you want to use, sine, cosine, or tan. All right? Think about in this triangle, is there anything that's not changing? And if we're talking about a fishing line right here, this being reeled in, this is changing. All right? They're pulling that fishing reel in. And this distance is changing too. If they're pulling that in, it's getting closer and closer. The bridge, though, is not changing. So I strongly suggest using the Y. All right. And think about according to SOHCAHTOA, this is opposite, this is adjacent, this is hypotenuse. All right. So if I want to use opposite, we're definitely not using cosine. And then we know dz dt, so we probably want to use Z. So we want to use opposite and hypotenuse. We want to use sine. So sine's probably going to be the easiest. So sine theta is opposite over hypotenuse. All right, our opposite is 15. We're allowed to plug that number in, right, because it's not changing. The height of the bridge is not changing. All right, our hypotenuse, we're going to have to call that Z for now. That's changing. That's that fishing reel or fishing line that's being reeled in. All right, so we need to take the derivative of this with respect to t. I'm going to put, actually, I don't think that'll help us. Let's rewrite this. This is Z to the first power right here. I'd probably bring this to the numerator to make it a little bit easier. All right, call it 15Z to the negative 1. And then I would take the derivative of that with respect to t. So derivative of sine is cosine. And then you'd get a d theta dt. If we bring the negative 1 out in front, we get negative 15 z to the negative second times dz dt. All right, so our cosine, we need to find our cosine. You guys know cosine is adjacent over hypotenuse. So let me highlight that. Cosine, right, is adjacent over hypotenuse. So 20 over 25 times d theta dt, that's what we're solving for. We got negative 15. I would probably bring this to the denominator. Call it z squared. if you bring it to the denominator, right, I left the z blank. That would be the z right there. But we know what z is. Z is 25. So I might substitute in a 25 there. And then we're multiplying by dz dt, which we know is -1. All right, so we can do some simplifying here. First of all, to get d theta dt by itself, we're going to divide both sides by 20 over 25. So we would get d theta dt equals, on the top, we'd get positive 15 over 25 squared, all over 20 over 25. All right, and if we do the outside-inside trick with that, we're going to get 15 times 25 on top. On bottom, we're going to get 20 times 25 squared. All right, there's a 25 on top and two 25s on bottom, so we could cancel a 25 on top with one on bottom, and it looks like we'd end up with 15 over 20 times 25, which is 500. And that probably reduces, so we'd get d theta dt, if we reduce that in a calculator, 15 over 500, we get 3 over 100. And the units would be radians per, in this problem we're talking about seconds. Radians per second would be that answer. So let's find the absolute maximum of secant of x on the interval pi over 2 to 3 pi over 2. So first of all, this is a open interval with those parentheses. All right, so this means we're going to do a sign chart. All right, a first derivative sign chart to be exact. All right, so that means we need to take the first derivative. So step one, if f of x is secant of x, if you don't know the derivative of that, you could rewrite that as 1 over cosine of x. That might make it a little bit easier. All right, so if we take the derivative of that, I'm going to use quotient rule. All right, our low, d high, the derivative of 1 is 0, minus high, d low, the derivative of cosine is negative sine, all over low squared. All right, and I'm going to simplify that. Cosine times 0, 0, that goes away. Double negative turns to a positive. So you really get sine all over cosine squared. All right, and from there, you have to set that equal to 0 and solve. All right, to solve this, I'd put that over 1 and cross multiply. You'd get sine of x equals 0. And think about on your unit circle, where is your sine 0? Think about your points. This is 0. This is pi over 2. This is pi. This is 3 pi over 2 and 2 pi. Those points are 1, 0, 0, 1, -1, 0, and 0, -1. So if we're talking about where is our sine or our y value 0, here and here, but they only want on the interval, remember, pi over 2 to 3 pi over 2. So we're really only talking from pi over 2 to 3 pi over 2. So the only value there is actually at pi. So x would be pi, would be a critical point. All right, but remember, critical points are where your derivative equals 0, but it's also where your derivative is undefined. So we need to double check that. Your derivative is undefined where your denominator equals 0. So we could take that denominator and also set that equal to 0. So to get rid of the square, you could square root both sides. You get cosine equals 0. And now think about, where is cosine 0? All right, cosine is your x. Where is your x value 0? Here and here. All right, but again, we're only talking about the interval pi over 2 to 3 pi over 2. And it doesn't include either of those. Pi over 2 to 3 pi over 2, only the stuff in the middle. So really, you cannot get an answer there. Because it doesn't include pi over 2 or 3 pi over 2. It's only the stuff in the middle, and that's because of the parentheses up here. So our derivative is never undefined on this interval, so our only critical point is at pi. All right, so step 2 is going to be a sign chart. Be careful with this sign chart. They had a very specific interval. All right, It's of our first derivative, but we were talking about the interval from pi over 2 to 3 pi over 2 only, and our only critical point was pi. All right, and we want to know, is our derivative, positive or negative on these intervals? So we need to pick numbers, all right, in between pi over 2 and pi, and we need to plug them into our derivative, which is this right here. All right, so we need to pick basically a number, all right, in between pi over 2 and pi, something in this second quadrant, all right? So we could pick a number, or we could just think about this. And it might be easier to think about it. Think about in your second quadrant, you guys know the saying, all students take calculus, right? In the second quadrant, sign is positive. So no matter what we would plug in, the numerator would be positive, all right? And the denominator, cosine, would be negative, but that would be getting squared. So a negative squared really turns out to be a positive, all right? So overall, that is a positive. And if we do the same thing now, all right, for between pi and 3 pi over 2, between pi and 3 pi over 2, that's this quadrant right here, all right? In that quadrant, right, if we're picking any angle, all right, tan is positive there, everything else is negative. So our sine value, our numerator would be negative, all right? Our denominator, cosine, would be negative squared, but again, a negative squared really turns out to be a positive. So a negative divided by a positive is going to be a negative. All right, so let's look at what our goal was. They wanted us to find the absolute maximum. So maximum is where our derivative changes from positive to negative. The absolute maximum is at pi. All right, notice they said find the absolute maximum. All right, they didn't just say the x value. We have the x value. All right, it's happening at x equals pi. We need to find the y value that goes with it. So you have to plug pi back into our original function. So the last step, step 3, we got to find f of pi, which is secant of pi, plugging it back into the original function. If you don't know what secant of pi is, maybe rewrite it as 1 over cosine of pi. Your cosine at pi, or your x value at pi, is -1. So 1 over -1, or -1. So we plugged in a pi, we got out a -1, so our point is pi -1. That is where our absolute maximum is. All right, I hope you guys found this video helpful.